Yeah, welcome back to Reinforcement Learning Part 2. So here we will consider the model-free case, which means that these probabilities we used before, the transition probabilities, the policy probabilities, are not available. I mean, let's say the policy might be available because it's under our control, but the reward function and the conditional probabilities, transition from S to S prime, these probabilities are not known. But we can generate data from the real system, the real world, so maybe a robot we want to optimize, or a simulation of the real world. And today we will, or in this whole lecture, we will consider only simulation, because often the real system it's not so easy to get data from the real system, so you first build a simulator and then work on the simulator, but of course people also apply it then to the real world data, and we will learn a little bit how this can be done. Also, some of the discussed algorithms involve the multiplication of a vector with a transition matrix, and this is costly and should be avoided, and the trick is to only explore relevant regions in state space. So the number of states can be quite large, and the transition matrix would be then the same dimension as the number of states. So this is can be too large to globally optimize with the equations we discussed so far. So here we are considering Monte Carlo methods, MC, and temporal difference learning, TD. So if you also look at the slides from Silver, it would be in lecture 4. And there are different strategies, and here's sort of an overview of different strategies how to apply reinforcement learning to the model-free case. So the first approach is evaluation. So estimate the value function or the Q function from a simulation. The simulation or the data from this simulation is sometimes also called experience. And we will talk about TD0 and SARSA policy evaluation. Or also in analog to what we discussed last time, optimization, learn an optimal policy. Here we have the SARSA algorithm or Q-learning available. In general, in this part 2, we focus on table representations. So we are looking at state spaces and transition matrices in state space. So the states or the probabilities over states is a vector, and the transition probabilities are a matrix. In part 3, we will consider function approximation like neural networks. Then obviously one could model the system and then apply previous approaches, so the approaches from last lecture. This will be covered in part 3, and an example where this is done is DINA. So if you first learn these transition probabilities and you have a good model of them and the reward function, then you can of course also apply the previous equations. Then it's possible to directly optimize the policy, which the policy is the controller. And the most important algorithm here is policy gradient, which is an example of direct policy search. And this will also be covered in part 3. In combination with Q-learning, it's the algorithm is called actor-critic algorithm. Then obviously one could also copy an existing controller, and the existing controller might be a human being. This is called imitation learning, and a related approach is called inverse reinforcement learning. Here are other important notions. So the behavior policy is the policy actually used in the simulation. So if you get data from a simulation, you have to also use some sort of policy, and the policy you're using actually in the simulation is called behavior policy. So states and state transitions and rewards are observed by using the behavior policy. There's also the target policy, and this is the policy we are optimizing. And this might not be actually the policy which is used in the simulation. So that's why people make the distinction between behavior policy and target policy. And some algorithms permit that the target policy is different from the behavior policy. The term on policy means that they are the same. The target policy is the same as a behavior policy, or at least, I mean, if you improve the target policy, at some point you will also pretty quickly try to get new data in a new simulation with a new policy. TD0 and SARSA policy evaluation and also the SARSA algorithm are on policy methods. And then there are off policy, where the target policy can be different from the behavior policy. Q-learning is maybe the most famous algorithm which works with off policy. But if we use a technique called importance sampling, we can also use other approaches offline as well. We will so have a short discussion on this in the appendix, but it's a little bit too much for the main part of the lecture today. Then another notion is offline. Offline means you actually only create data in a simulation and then use that data for policy evaluation or Q-learning. And for example, these two algorithms, policy evaluation, you don't have to change the policy at all, but you use the policy as a behavior policy, and then you can do one big simulation and just never simulate again. So that's sort of offline. Here's I mentioned a biological aspect that some people argue that the brain also stores data in an offline manner as an experience, and then use that to optimize algorithms like reinforcement learning. Okay, but that's just a side remark. Online means the updates use the data from the actual simulation without storing the latter. So online approaches are often considered biologically more plausible because if you think you're an agent, maybe a simple agent, and you might not have a big memory storage capability, and you don't have a good way of accessing this big memory. The only thing you're left with is sort of working with the experience or with the data you are sort of collecting online, and you're also doing the optimization online. And some algorithms permit that. Then there's the notion of an episode. So the simplest idea of an episode is a game. So you start maybe a game of chess, and then at some point it will be terminated if one party wins. And then you do another game of chess. And these games are called episodes. So the actual sequence is stored in order, but learning doesn't always need to follow the sequence. Sometimes you can randomly change the data, and then you don't have to follow the episodic sequence in training. But some methods you have to follow the episodes. For example, if you use recurrent neural networks for training or for modeling, or so-called eligibility traces, there you have to be careful and you have to follow the actual sequence of events also in training. So we start with Monte Carlo policy evaluation, and the goal is to estimate the value function of an unknown MDP under a fixed policy. So we don't have, as I said, the P's, the probabilities, but we can get data from a simulation. In the simplest form, we simulate the system and we register when state S is observed and calculate the discounted reward a number of steps in the future, or until the end of the game, or maybe some finite horizon. So let's assume that state S was observed at time t, and we define the return, also introduced in Silver, as so at time t, the state S, and then we are just collecting all the future rewards from time t onwards, and where we also use a discount factor gamma, so we end up with a finite sum. So we multiply by gamma and then gamma to the power of t minus 1. And the expected value of that actually, of course, is the value function. So the expected return is the same as what we called value function before. So and then we update. So S was. In S we are accumulating the experience, so the return, the actually observed return, in the simulation. So this is not an expected value, these are the actual observed returns. And then each time we are in state S, we also update this NS and increment it by 1. And eventually, after we did enough simulation, the V pi, so the value function for this policy of state S, is S of S, so the sum of all these returns divided by the number of times we observed state S. And we are using these capital letters, and we're following also Silver here, for quantities derived from data, and lowercase letters as before, the V and Q, for quantities derived from the true model. I mean, it's sort of almost the same, but maybe this distinction makes sense and is important sometimes. Yeah, so the small r is the rt plus 1 is the actually observed reward at t plus 1. So MC needs episodic data, because to estimate this return, of course, we have to know which order these rewards had occurred. And an analysis shows that it has zero bias, so there's no distortion, or in our definition of bias before. So on average, it will give you the correct estimate, but high variance, so it might need quite a lot of data to get the value function correct. Thus, conversions might be slow, and it does not exploit bootstrapping, as we have seen before in value iteration and similar methods or evaluation methods. V was always the function of the previous V, or Q was the function of the previous Q, so this is called bootstrapping. Also works when the Markov property is violated, so it gives you also a certain notion of robustness. The simulation must be on policy, and of course we for the value function for the policy we want to get the value function for a particular policy, and this policy must be applied in the simulation. But the simulation can be offline. That means you can do one big simulation and then estimate just from all this collected data. Now we can also incrementally update the value function. So let's say at time t the system was in state S. So and we can update our v of s. So this is the previous v of s, and we multiply it by ns and divide by ns plus 1. So it's a little bit less than 1 here. And the new return at s prime, we also divide by the same number, ns plus 1. And so this is, if you think about this, sort of an online version of this algorithm here. And we can write this. We get rid of this term here by moving it to the right. So it's the same as vs plus 1 over ns plus 1 times the difference of the return at s prime minus v of s. S prime always means the following state. So if you add this together with this, you get exactly this expression. And now we approximate for this return here as the actual return plus gamma times the value function of s prime. So we can write this update here as vs, so the new vs is the old vs, plus the learning rate eta times r prime minus gamma, the value function of s prime minus the value function of s. Okay, let's look at this equation again. So the update is the new value at s is the old value at s plus learning rate, and then the observed reward r prime plus gamma times the value function at s prime, so at the next state, minus v of s. And this is called the TD0 update of the value function. You can also start from our previous definition. By the way, this algorithm was invented by Rich Sutton in 1988. Now we can also start with from our policy evaluation equation. So now we have with the probabilities we use the small letters, lowercase letters. So v of s is the return function here, or the reward function. Under the policy plus gamma times the transition and the following state v of s prime. And the right side we can approximate this by a sample. So this is an expected value of the observed return on this r prime, and gamma times the follow-up state if we are doing a simulation. So an unbiased sample now is this guy here on the right, r prime plus gamma v pi of s prime. So now we are using the approximation from the data, and this gives us TD0, which is an approximation or is a form of policy evaluation, and we discussed this equation before. The difference here, so eta, the bracket goes from here to here, is called the TD error, and eta is a learning rate. Actually, in training, we can also randomly change the order of the observations. So we can do stochastic gradient descent, because the data point is really the triple, the state at t, the state at t plus 1, the reward, and the reward which was actually observed. And if you keep that together, then you can train it in random order. You don't have to follow the actual sequence of events. So TD0 is used on policy. Now, obviously, we want to evaluate a policy, and then we have to also simulate with that policy, but it can be used offline. In this way, we could update our value function until some form of convergence. But TD can also be used online. If you think of progressing in time, you can also use this update with actually data occurring at time instances. And this is, as I mentioned before, is considered biologically more plausible. TD uses bootstrapping because the next value function is sort of derived from the old value function, and also this TD error contains the old estimate, so it sort of improves on itself. It's considered to have low variance, so it needs fewer data points, but might have some bias. There's also a term called backup, which denotes how far the future is explored, and TD0 only one step in Monte Carlo until the end of the simulation, big T. There are also some variants, and I want to just briefly mention it. We will not discuss it. So there's something called TD lambda, where lambda can be between 0 and 1. And TD0 is the algorithm we just discussed. And TD1 is similar to the Monte Carlo approach. And lambda in between sort of mixes both advantages. And it includes something called eligibility traces. But we will not cover this in this lecture. But if you're eager to learn about it, you can look at the slides from Silver or the book from Sutton and Berto. We can also derive a similar algorithm for the Q function for policy evaluation. So instead of estimating the value function, we are estimating the Q function for a given policy. So now the target is the return plus gamma times the Q function of the following state and the following action, and we can update using a very similar equation as TD0. So the new Q function is the old Q function plus learning rate. And then here's the observed return plus gamma, the Q function in the following situation, minus Q of SA. Again, we can use a random order of presenting this data, where a data point consists of the quadruple, so the state at t, the action at t, the state at t plus 1, and the action performed at t plus 1, and the return, of course, at t plus 1 prime. So SARSA policy evaluation is on policy. So you have to get the data from the policy you want to evaluate, but can be used offline again as TD0 as well. So now we are looking at policy improvement, or how do we get a better controller or policy with these observed data. So let's first look at value iteration. Now remember, we discussed policy iteration and value iteration, and value iteration had some advantages because the learning and the modeling was sort of done together, and the optimization and the modeling. But there's a problem with the immediate application of value iteration. For example, if you look at the update here of the value function, we have to maximize over actions. And if we want to approximate this term here by a sample, I mean, actually we have committed to a certain action, which is the one which we did in the simulation. And so we cannot, also another reason is, I mean, maximizing over samples would also be difficult. It might be very noisy estimate. So this does not work immediately like this. Only if there's a certain model structure, then this can be applied. And we will discuss this in the appendix. The important term here is the after state. So in general, this is we cannot do this, but in some cases we can. So we are now defining a specific policy, P epsilon, which uses so-called epsilon greedy exploration. So essentially, it is probably a policy which works like that. So assuming we have a Q function, or a current version of a Q function, Q S and A, so some Q function which occurs in the course of the optimization, and with the probability 1 minus epsilon, we choose the action which is optimal under the current Q function. So this is the best action we can do under the assumption that the Q function is correct. So we're saying policy is greedy on the Q function. But with probability epsilon, we choose a random action. So we also permit other choices. And this is important because if we are always using the action which maximizes the Q function, we are not really exploring the system very well, or the simulation very well. So this means we are in general following the action which is implied by the Q function, but occasionally we do a random action. And of course, this might be a problem in some applications where you're not allowed to do random actions, it might destroy the plant. But of course, there are variants on this idea. And then there's the Q policy improvement SARSA, a policy iteration SARSA algorithm, yeah, so we are using the epsilon greedy policy pi epsilon, and then we use the SARSA policy evaluation to estimate the Q function, which belongs to this policy. So if we have a policy, and in this case it's a random policy or it's a probabilistic policy, so there's for given state we can use different actions, then we can evaluate the policy and get the Q function using the SARSA policy evaluation. And by switching forth and back to doing the SARSA policy evaluation to get the Q function of the new policy, and then applying epsilon greedy to define a new policy, each time we change the Q function, the epsilon greedy policy changes, and vice versa. So we have to iterate forth and back. And this is called the SARSA algorithm. And SARSA is on policy because each time we are optimizing, or we have changed the Q function, we have to do another simulation to get new data for the new epsilon greedy policy. Then there's the famous Q-learning algorithm. So recall before we had this equation, when we knew the probabilities and the reward function here, we could apply this update, and we can now get a sample or one sample approximation here from the right side in the same spirit as before, as being the observed reward plus gamma, and then the max over the Q function here from the following state. And this leads us to Q-learning, which was one of the major breakthroughs in reinforcement learning from Chris Watkins in 1989. And he uses exactly this this as a target here. So the new Q function at SNA is the old one plus eta, the reward plus gamma, and here we're doing the max here, and this is not hurting because there's no sampling involved. It evaluates the actual Q function, so this maximization is not harmful, minus the current value of the Q function. Again, we can use it in random order, and a data point would be a quadruple: the state, the action, the following state, and the following action. And the reward, sorry. The simulation can be off policy and offline. So maybe a little bit surprising, we don't in principle have to redo the simulation. We can do it with one behavior policy, and the target policy can change in this by doing the Q function updates. And the reason is that in the simulation we are essentially simulating on something given an action or given. We don't have to. We're not using the follow-up state because we are maximizing over the follow-up state. So we are not insisting that we are following a policy. So we can. That's why we can use the data in a simulation with a certain Q function, a certain policy, to iterate in this fashion. And this can be relevant in safety critical applications where one is only able to observe the system under control, so under a certain policy. So in principle we can do it. In practice we have to do also get data from a new policy, because if we are just blindly using these equations, we are sort of getting into state spaces which were not really simulated. So in principle we can do offline off-policy learning, but actually Q-learning is combined with this epsilon greedy policy, which then simulates new data or get new data from a new simulation. But in principle this statement is true. I might have gotten it from Wikipedia, I don't remember. SARSA and Q-learning are both reinforcement learning algorithms that work in a similar way. The most striking difference is that SARSA is on policy while Q-learning is off policy. Because as I said in this update equation, it's not necessary that we follow a particular policy. No. Yeah, so in principle, in practice, we are also changing the behavior policy with the greedy policy, epsilon greedy policy, and change these two iterations. And at the end, after everything has converged, then we're doing a deterministic policy which is greedy on the Q function. So now in part 3, we are actually then considering the case that we are using neural networks, and we will also talk about the tricks used in games, in the spectacular successes of DeepMind and AlphaGo, AlphaZero, and so on. So, as discussed, the value function, the Q function, or the policy, they can all be high dimensional. And so far, we assumed that these three can be represented as stable lookups. So maybe pi of s is a vector, but a probabilistic one, also would be a matrix from S and A, or value function is a vector, Q function is an array, and if S is high dimensional, this can become an issue. And this is not harmless, so Go has 10 to the 170,000 states, and this number would be impossible or a table of the size would be impossible to store on a computer. Also S, so the state, can be represented by a number of input variables. For example, the position of a specific robot parts, or angles, or velocities, and so on. In the notation, we will keep using S most of the times, not always, but consider that the value function of S, for example, could be a parameterized function of S, and it could be a parameterized function of future variables x1 to xm. Yeah? And the right side looks already more like a neural network, for example. So, but you can sort of generate the states S out of these variables, at least when these variables are one-hot vectors. So M1 hot vectors should be there. And then S, and S is also one hot vector. Then S can be considered a tensor product of the individual representations. But this is a little bit advanced and we don't really use that. But it's important that we don't always have to go into the state-based or explicit state-based representation. We can also use variables as we have done before all the time. No? So now we have real inputs and we are learning a mapping. And V of S can be represented as basis functions. So actually basis functions and features, or feature functions, so these would be features. Mathematically it doesn't make a big difference. No? But of course you can also represent it as a neural network, and then it makes a difference, no? Because basis functions is just another transformation of the features, as we have discussed before. So we can map the inputs to M5 basis functions, and then we need to learn the map using these basis functions to value, for example. And then we can also think of them as features, these x's that describe the states, as I mentioned before. And to maintain the Markov property, it should in principle be possible to restore the state from the feature. And so if you have to, if the number of features is not large enough, you might not really be able to determine the state, and that's another big issue in reinforcement learning. If the states are partially observable, but we will not cover it in this lecture. But of course we know with basis function the parameters enter linearly in the model, and this is sometimes quite nice. But we can also use a neural network instead of basis functions to have the map from the features, from the x's, for example, to the value function. So here's an update, or a TD0 update for a neural network representation, and we are simply using this notation here, V sub W of S, so it means it's a function which is parameterized by parameters W, can be a neural network, but typically here we would consider either basis functions or feature inputs, but for notational simplicity we're always using this S notation. And then we can do a parameter update for, let's say, WK. So WK would be one of these elements in this vector. It's the old one, plus learning rate, then the TD target, so R prime plus gamma times V of S prime of the following state. And I'm using this W minus notation to indicate that this is not the term we calculate the gradient with respect, but we do it with respect to this second term, and get here the partial derivative of the value function at S with respect to this parameter. Now, recall that this might be a neural network. So this is the TD target with the current parameter estimates. That's why I use this minus notation. And the gradient is calculated with respect to the VWS. And this generalizes to SARSA policy evaluation, Q-learning, and SARSA, also the SARSA algorithm. So we always get these type of update rules for the parameters now in a value function or in a Q function, for example. Then one of the tricks which are used is this experience replay with fixed Q targets. So Q-learning, as described, has sometimes convergence problems, in particular when used together with neural networks, and even more specifically with deep neural networks. So deep Q networks, or DQNs, they are sometimes called. Also historically, so part one, what we discussed last time, sort of part of dynamic programming or optimization in Markov decision processes, and then in the early 90s people did the TD0 and Q-learning was a little bit, no, 89 I guess, also in the 90s, and then people also used function approximators like neural networks, but it was one of these things, now very difficult to get it to work with the computational power available at that time, and Q-learning, for example, had a lot of convergence issues. So it was like with some of the other things like recurrent neural networks, where people weren't really sure if this stuff was working, and in practice there were simply a lot of problems which were difficult to solve. So I think also in the course of the 90s, the interest in reinforcement learning sort of decayed a bit. There were always some sort of revivals, but the serious revival also came with DeepMind and all these successes in game playing. And this is, so for example, one of the tricks they're using. So experience is a random subset of the simulation. We discussed this before. And we are using fixed Q targets. So that's why I'm again using this minus notation. So this is the target as derived before in Q-learning. But then we consider this as sort of an offline problem. And we sample random mini batches from the simulation, and the samples should not be in sequence, they should actually be random, as I said here. And then we are simply defining a cost function, which is the square difference of the Q target and the Q function. Yeah, so the QS and A. And now we have a normal cost function we can optimize with several steps and with respect to the Q function here with the W parameter. And this is called experience replay, now because we're using this sort of offline data with fixed Q targets, because these are considered fixed. And doing this is, it looks like a well-known regression problem, or at least squares problem, so you might already have the feeling that this might work quite well. And so the cost function minimizes squared error. This is called also least squares Q-learning. And sampling a random subset is important to reduce correlation. If you take always like sequential batches, it doesn't work so well. And then, of course, occasionally you're doing an update on the Q function, and then the the targets are defined by the updated Q function. And note that, this is the least squares problem, so if this is a sum of basis functions, then we know that we can get explicit solutions for the weights on the basis functions. So this, of course, is also nice. Now we can do it in one big step. to learn the parameters, how you do. There's simple linear regression, maybe in high dimensions, so you might still want to do stochastic gradient descent, but you sort of might have the feeling already that this is quite nice and stable. The behavior policy during learning is also epsilon greedy with respect to the current Q function. Then another idea, so now we are sort of, for a moment, we are leaving the Q functions, the value functions, that we are trying to get a model of the system. So if we had a good model, this was discussed last time in part 1, then we have this P, the probabilities, and we can use the algorithms from last time. But if you don't have these p-values, maybe you can estimate them. So it's a very straightforward, simple idea. But of course, system identification has a lot of problems on its own, because, for example, if your system works under some control, which it often does, you don't want to break your system, then you're also only exploring maybe a small part of the state space, and your model might not be reliable everywhere. But the idea is to learn a model for P as prime given S and A, which predicts the probability distribution, and learn the reward function as a regression problem. Of course, it's not clear that a good policy for the learned model based on simulated data is also good for the true model, because of course reinforcement learning is very smart in exploring certain properties of your model, and if your model is not very good, it might explore some properties of your model which is not really there in the true system. If P S prime given SA is a table representation, it's a three-way array, which would be nice, but sometimes this is simply too big. And modeling this transition probability when S and S prime are presented as features, it's not trivial. And people explore, for example, graphical models or generalized linear models, or you make strong model assumptions and assume a joint Gaussian distribution. Or if you only need to simulate from the model and you don't need the p values, so the probabilities themselves, you can use maybe something like a GAN model. So it looks attractive, but there are some serious technical problems here, really. So approach 1 in DYNA is, DYNA probably comes from dynamic programming. So do the modeling and then simply use the learned model in value iteration or policy iteration in the way we discussed last time, the first lecture. And approach 2 is actually then sampling data from the model, and maybe then also mixing in data from the new simulation. So maybe you mix different data sets, or I guess that's version 3, yeah. Okay, one would be to use the probabilities, the P's, in dynamic programming. The approach 2 would be to simulate then data from the model and do a reinforcement learning based on the simulation from the model. And approach 3 is to mix the two data sets, the one from the real experience and from the simulated experience. So this is covered in silver in the lecture 8. Another idea, as we mentioned briefly before, is imitation learning. So you have an existing controller, which is a map from maybe from state to action, and maybe this controller is a human being, and you learn this policy or this controller just by imitating the existing controller. It's called imitation learning or apprentice learning. Instead of copying or learning from a human controller, a teacher directly also can try to learn the reward function of this controller or of this teacher And so we can sort of invert this process. Typically we start with the policy and then look at the reward function, but maybe we can learn the reward function by observing people and then infer the other things we are interested in. And that's called inverse reinforcement learning, and it had some spectacular successes in the control of a toy helicopter. So it was a pretty impressive demonstration, and it uses this type of reinforcement learning. I think it's considered not to be very easy to use, inverse reinforcement learning. So I'm not sure what the active research agenda there is, but in some cases it was quite successful. So here's another important algorithm for reinforcement learning: direct policy search and policy gradient. So pure Q-learning works well in complete discrete domains, for example, board games, but not as well in continuous domains like in robotics. Example, control of a robot arm movement. So in direct policy search and particular policy gradient, it's a robust reinforcement learning algorithm which you might want to apply to a novel problem, and where you don't want to deal with the complexity of value functions and Q functions. So it is pretty simple and straightforward and works quite robustly. So that it's a really a major an algorithm of major importance. And the idea is to directly optimize the parameterized policy or controller. So P theta action given state. And this is called direct policy search. And to have an idea of what this policy might look like, so the conditional probability of the action given the state might be a softmax of this action, and based on a function vector parameterized by theta applied to some input variables. So it's a neural network with a softmax output, for example. In Silver, it's captured in or covered in lecture 7. As I said, robust convergence properties, effective and high-dimensional and continuous action spaces, and also can learn stochastic policies. So it really has a lot of advantages. There are also some disadvantages. I mean, it has issues with local optima, and yeah, it has some inefficiency and high variance, but these are, I mean, the advantages are really quite impressive. So the score is typically given by a Monte Carlo simulation, and I mean, Monte Carlo estimate of the return, for example, or the value function. I mean, you can try to apply gradient-free methods. So essentially, you for a new policy of a varied policy, you can calculate the value function of that policy, and then simply vary the parameter in a controller, and sort of try to improve step by step the parameters in the policy or in the controller. So you can use hill climbing, simplex, genetic algorithms, and so on. Or one can approximate the gradient of the cost function with respect to the parameter by finite differences. But maybe the most important one is a policy gradient, which we will cover now. And it's a basis for calculating an approximate gradient. So I'm trying to derive it here. So let's say we start at t0 and we are in some state s0. Now we are considering the expected reward at some future time tau. So we start at 0, but now we're looking at tau. So we are interested in the expected value of r tau. And this expected value is the sum over the values of r, and then the sum over r times the probability that r is observed at time tau, starting from s0. We can now try to calculate the gradient with respect to a parameter in the policy. So we're taking this expected value and taking the derivative with respect to the parameter. Then we are substituting this equation, so it's the sum over r of r and then the partial derivative of the probability that r is observed at time tau, given as 0. And this is can be written in this form, and here we are using the log trick discussed in the beginning, because the derivative of something with respect to the parameter is the derivative with respect to the log of the argument times the argument. So that's in the very beginning of the slide set I discussed this. And the advantage is that, two advantages. One is we now have something like an expected value here, because we are weighing it by this probability. And also the log, so this is sort of derived from a big product of terms, and the log is then decomposes into the sum of terms. So it has these two big advantages. And if we are considering the gradient, because now this is the sum of many terms, we only have to keep track of the terms where the policy is really involved. And so all the other transitions we can ignore because they are not directly dependent on the theta. So this is a great simplification and a pretty amazing trick, really. So now, since all these terms disappear, the derivative is again the sum over r, and then r times the probability that r is observed given as 0. And now we have the derivative from time 0 to tau minus 1 of the log of the probability of the action given the state. And this can now be approximated by Monte Carlo, because this is a probability. We can simulate this. And we can approximate this by the observed return at time tau. And here we have a sum from 0 to tau minus 1 of the derivative of the log of the probability of the action given the state. And this is quite a simple algorithm. And we don't have to do backpropagation of time or anything. It comes from the beauty of this Monte Carlo approximation. And these are also the actually observed actions and states, AT and R tau. Now, of course, we are interested in the derivative with respect to all future returns from R1, R2, and so on. And we just have to now add the sum here over the different taus. And we keep the second term. And now we sort of change the order of the summation. And this is now a sum over all time steps. And here is a sum over from t plus 1 on over the returns. And this is the gradient at this time step. And this is now quite suitable to a sample update algorithm, and it's called reinforce from Williams from 1992. And the update is that the no parameter is the old parameter times the learning rate. And then here we have the sum over future returns. And then we take the derivative of the action at this time instant also on the policy of applied to that time instance with respect to the parameter. Typically, we are also using a discount factor, but for simplicity, I didn't include the discount factor. But now, I mean, sort of, I hope you can appreciate the simplicity and the beauty of the algorithm, no? Because this term here on the right means essentially that we are taking the action which was part of the simulation as the true target, no? So essentially the simulation gives you the target. But that seems to be strange. Why should we try to like sort of model the sequence of observation in the Monte Carlo process? We want to optimize the controller. And this is done by this weighing here. So if an action had a consequence which was quite positive, then this graded step gets a larger weight. And if the consequence was not so good, it gets a smaller weight. So it's more obvious when you enter the discount factor that this effect occurs. So it's really a simple and very beautiful algorithm. And as I said, it's quite robust. And so my personal experience is that I always considered reinforcement learning to be extremely difficult and difficult to apply, and you have to spend a lot of time to get it to work, to have convergence and so on. But then another group of my students were using reinforcement learning in the application, and the reinforcement learning part was not a major part of that application. It was a completely different focus. And then I was very surprised, and I asked them, but how did you get it to work? Why is it? Why didn't you have to spend all the time of optimizing your reinforcement learning algorithm? And it turned out they used policy gradient, and policy gradient has this type of robustness. So it is really a huge asset in our toolbox of algorithms. And there are many different variants on that. A famous one is the actor critic, or the Q actor critic here, where essentially we are. So this is what I'm writing here is something like a value function. But you can also use a Q function in this location. So instead of like waiting for the feature rewards, you're using your estimated Q function. And actor critic is a very popular and powerful algorithm used in many applications. Okay, finally, I want to discuss a few of the additional tricks and approaches used in the amazing successes on the use of reinforcement learning in board games. So one thing they are often using is Monte Carlo search. So assume a learned model and a policy pi. The current state is sub t. Then they simulate k episodes until the end of the episode at time t, and estimate the Q function based on the mean returns. And let's see. Select the one action which corresponds to the one action which maximizes the Q function. And many games now with amazing computational power available, simple Monte Carlo search is sufficient, for example in Scrabble or also in backgammon. And there's a variant called Monte Carlo tree search, MCTS. It's a combination of tree policy and default policy. It works for black box models, so it only requires samples, and it's computationally efficient and can be parallelized. And MCTS is the best performing method in many challenging games, for example Go. But typically people use a variety of strategies together. Something special about games is that you are, or the agent is playing against an opponent. No? I mean, so far the assumption was sort of that nature was random but neutral, so it didn't really try to beat you in any sense. In contrast, in a game, one is playing against an opponent, so somebody, and sometimes you have this zero-sum situation where there's some reward to be shared between the two players, and if one gains, the other one loses. If the policy of your opponent is fixed, the problem reduces to a normal Markov decision problem. So the other player becomes part of the environment. But if both are optimizing jointly, the analysis becomes more complex. In a so-called Nash equilibrium, which is one of the central concepts in games theory, none of the rational players would choose to deviate from her or his policy. And this is the concept behind self-play reinforcement learning. A reinforcement learning agent playing against itself. So at the end, sort of both agents pursue a rational strategy and converge to a Nash equilibrium where it doesn't make sense for either of them to deviate from the strategy. One of the early really important breakthroughs was TD Gammon. Before that, there was the checkers playing program from Arthur Samuel in 1959. I remember he was there at this Dartmouth workshop where AI was formed. And TD Gammon is a computer backgammon program developed in 1992 by Gerald Tesoro. It's based on TD0, and already then a neural network was used for a function approximation, and it uses this trick of after-state evaluation. And historically, this was extremely important. In many ways. At that time, it looked like reinforcement learning moved from academia to serious applications, and it is a very important success. TD Gammon was chosen because of the randomness in the throwing of the dice, which where reinforcement learning has no problems with, but other approaches would be much more difficult to handle this problem. So and also it was one of these landmark successes which got a lot of companies interested in reinforcement learning. Also, our team did some projects in reinforcement learning. We had a collaboration with MIT. Unfortunately, it turned out that it only worked for TD Gammon in a serious way. Now, of course, there are toy problems and all sorts of problems academia works with, but the success of TD Gammon at that time could not be generalized to real-world problems. I mean, in a way, the situation today is a little bit similar, maybe not quite as black and white, but as a very important success in reinforcement learning, it really stands out. Then AlphaGo was a huge success by the company DeepMind. It plays the board game Go, and Go was or is considered to be one of the most difficult games to play because of the huge search space. So it first does some form of imitation learning or apprentice learning. So now we're talking about 2016. So the policy network is trained by copying humans, so by learning from human moves, bootstrapping from human gameplay expertise by supervised learning. This provides fast, efficient learning updates with immediate feedback and high quality gradients. Then policy gradient was used. So reinforcement learning based policy network optimization and to rapidly sample actions during rollouts. Then experience replay with least squares was used. We remember we discussed before that experience replay. We discussed it in the context of queue functions, but it also works in other cases. It's quite stable and a powerful approach. And then also MCTS was used, guided by a value network and a policy network. And so it uses, policy gradient, of course. I don't know if I emphasized that. So policy gradient was used, and Monte Carlo tree search, and so it was really a combination of different approaches. Then AlphaGo 0. So 0 means it's optimized by self-play, no copying of an existing expert. It reached the level of AlphaGo Master in 21 days and exceeded all the old versions in 40 days. So Silver is the one who provided these slides. So he's one of the key people in these developments. So it didn't use bootstrapping from human gameplay expertise, and was pure self-play. So that was 2017. This was AlphaGo 0, so it was applied to the game of Go, and then Alpha 0 sort of can be applied to a large set of different games like chess, Yogi, and Go. So that was 2017. Earlier was Atari. Maybe that was the first success of DeepMind in this domain. And interesting here, it uses actually it reads the game as an image, so it uses convolutional layers, convolutional neural networks, or DQNs. So the agent had to learn from really looking at that. So there was no sort of parameterized representation. It was the visual input from the screen. Then a number of recent developments which might be of interest. So Mu0 is a computer program, also from 2020, by DeepMind, to master games without knowing their rules. It was trained via self-play with no access to rules, opening books or endgame tables. And the trained algorithm uses the same convolutional and residual algorithms as AlphaZero. So if you want to get more serious, there's an important toolbox platform called Stable Baseline. Has a set of improved implementations of reinforcement learning algorithms based on OpenAI baselines. There are some comments left I wanted to take out. So and recent advances in policy gradient and actor-critic algorithms, so-called SAC or ZAC, soft actor-critic, proximal policy optimization, PPO, and deep deterministic policy gradient, deep DPG. And I think they are all can be used in terms of sort of robotics applications with continuous state spaces. So if you want to get serious into in this direction, please look at the Stable Baseline platform or Toolbase. So reinforcement learning permits one to act better, maybe even optimally, so rationally. Oh yeah, here's another mentioning of DDPG, which is quite useful if there's continuous control. So if you don't have a softmax output, but maybe a control output, a linear output, because in continuous domains Q-learning is not as effective, as I mentioned before. Yeah, one thing we didn't discuss is that sometimes the state cannot be observed completely or reconstructed from the observed variables. That's the situation in partially observed Markov decision processes or POMDPs. Currently, it seems the solution is to use recurrent neural networks, but it's not part of this lecture and I didn't really read it up. So, but Silver has something on that. An ongoing topic is offline reinforcement learning, where you collect data, which you then use automatically or offline. Examples are BCQ, Beer, and Bruck. Yeah, 2 comments on the appendix. So here's the structure of the after state, or let's look at the graphics first. So there's a state after your move of so the move of the agent. Then there's the move of the opponent, which is from the viewpoint of the agent might be probabilistic, and goes to this after state S underscore. So this is the board game the agent is forcing. Then the agent does a policy, some action, and then there's a deterministic transition to the next board game. So this is the situation in many board games, and in that situation the value function is enough. So because the Q function of S and A is the same as the value function of S prime, evaluated deterministically on the after state and the action, and based on this one can do a greedy policy update by just taking the action as a policy which maximizes this quantity. So in that case, and this was for example used in backgammon, in TD gammon, you don't need to do Q learning. You value function learning is sufficient. And another comment on importance sampling. So we said that some algorithms require on-policy learning, like TD0, and but there's a general approach called importance sampling, which essentially is a correction to the fact that you are evaluating a policy which is not used in the simulation. So the pi is the policy we're interested in, but the simulation is on the mu policy, and it turns out that what you have to do, you have to introduce this correction factor when the data comes from the simulation of the behavior policy. You have to multiply it by the quotient of the 2 probabilities, and this is a very common approach in similar problems, and it's called importance sampling. So yeah, it's maybe an interesting update or add-on. It's probably not absolutely essential for the course of the lecture, but I thought I make a remark on that. So thank you very much for your attention.